Okay, what's up next? Graphing. There's a couple of different ways I could present this topic, um, but I'm going to present it in a way I think which will make it easiest to understand. So I think this should be worth your while watching this. That's the quadratic equation that all graphs of quadratic equations are based on. And its graph is going to look something, well, I'm sorry, its graph is going to be something that we call a parabola. And um, in a way, if you've seen one straight line, you've seen them all. If you've seen one square, you've seen them all. If you've seen a triangle, I mean, they're different, fine, but I mean, you get the idea of a triangle, you get the idea of a square, you get the idea of a straight line, you get the idea of a circle, and you're going to want to get the idea of a parabola, what it is, and what it looks like, and they're all based on this specific one. This is the quintessential example of a parabola. Now, how do you make a graph when you don't know how to make a graph? When all else has failed and all hope seems lost, you plot points and connect the dots. As I pointed out before, that's not very elegant, it's not very sophisticated, it's not very insightful, but it is the thing you can try to do when all else fails. So let's go ahead and do that. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. If x is 3, y is 9. 4, 5, 6, 7, 8, 9. Now, something you notice that's in the way is that this is going to get nearly impossible very fast. Write this over here. If x were to be 5, y would be 25, and that would be above the ceiling. If x was 10, y would be 100, so on and so forth. But what if x is negative 1? If x is negative 1, negative 1 squared is 1. If x is negative 2, 4. If x is negative 3, 9. And we shouldn't leave out fractions. If x is 1/2, 1/2. 1/2 squared is 1/4. So if x is 1/2, y is 1/4. If x is 1/3, y is 1/9. And what you get is this. Now, could you do a better job of graphing this? Absolutely. Get out some graph paper. If you go to Desmos or any graphing software, that's basically what it's doing. It's plotting points. It's plotting them more accurately. It's plotting them faster and more points. But this is the picture. Now, just so you know, you see parabolas around you, and the all-time classic one is if we neglect wind resistance. Throw something in the air. Take anything you have at hand that's a fairly dense object, a rock, a stone, a pencil. I guess I could do a marker. Look. Well, probably can't see that. But the path that it follows is a parabola, and if we neglect wind resistance, it's exactly a parabola. I'm not proving that. We'll have to save that for a calculus-based physics class to prove that that actually is the case, but it is. Go to a water fountain, turn on the water, and watch the water come up like this. It's forming a parabola. If you were to look at the mirror on a telescope, the mirror is parabolic in shape. If this was the mirror, I'm not proving any of this right now, but, If this was the mirror in the telescope, the cross-section of the mirror is a parabola. And it has the property that all incoming parallel rays of light reflect at the same point. Again, you can't actually prove this without calculus, but it is in fact true. And what I'm saying is that there are parabolas around you in life, whether you're aware of it or not. Now, they're not all this parabola, but they're all based on this parabola. And it occurs to me right now that what I should do is now, really now would be a great time to use Desmos. So I'm going to do something here on the board. And I suggest that what you do is go to, well, I would really suggest that you would make a hand graph. I'm not sure how confident I am that everyone's going to do that or anyone's going to do that. I wish it would be nice. So what I'm going to do by hand right now, it would be great. But you can certainly do it on something like Desmos. So what that is to graph, for example, this on the same set of XY coordinates and see how it compares. And what you would find is it would look like this. And the nice thing about Desmos, for example, is when you do this, it automatically will generate it with a different color. I don't have any different color markers right now. So what you would get is this. You would get the exact same parabola, but shifted up one. It's the exact same parabola. And if you do this on Desmos, for example, or any other graphic software, it will be pretty clear to you that it is the same parabola. In other words, this parabola is this parabola, but it's shifted up one. And if you did this, it would be crystal clear to you that it's the same parabola, but it's shifted down 5. And if you graph this, what you would see it is the same parabola, but it is shifted over one to the left. And if you were to graph this, say for example, it would be the same parabola shifted over to the right. So the left and the right shift, I think they go opposite or contrary to what you would think. The vertical shift, the up and down shift, do what you would expect. Now, finally, if we were to graph this, in fact, let me start again. This won't be legible here, so let me erase this. So let's say y equals 3x squared. If you graph this, what you would find is that it looks almost the same, except it's been squished up like this. It's steeper. So if this was the original parabola right here, y equals x squared, here, this is this parabola. And if you were to graph y equals, say for example, 1/4 x squared, it would look like this. So what's happened here is that we've taken the parabola and flattened it out. Finally, if you graphed this, y equals, say, negative 3x squared, you would get this. You get a mirror image of this across the x-axis. So the number in front, this coefficient, this number in front of x squared, it affects the relative steepness. Now, parabolas don't have slopes. They don't have slopes. If you get to calculus, you'll see we can make some sense out of that. But for right now, I'm just being, it's fairly, I was going to say vague. It's not really vague, but it's not really pinned down. But look, at any rate, I mean, that's a very steep parabola, and that's a very broadened out or not steep parabola. And this is an upward-facing parabola. This is a downward-facing parabola. The up and down is pretty straightforward. If the coefficient is negative, it's down. If the coefficient is positive, it's up. Including here, the coefficient is positive 1. And then if the coefficient is less than 1, it broadens out the parabola. If the coefficient is more than 1, it makes the parabola steeper. Okay. Now we can piece this all together, and it's going to make graphing parabolas remarkably easy. In fact, maybe strangely so. You might think, hey, wait a minute, this is too easy. What's the catch? And there is a catch. Yep, there is a catch. But if you want to graph this, let's say, let's see. How would I graph this? This tells me that I would go up 5, 1, 2, 3, 4, 5. This tells me to go over 2, 1, 2. and this tells me it curves down. Now, when I said goes up and over, what's going up and over to arrive here? Well, it's the vertex of the parabola. Now, in the original mother parabola, that was at lowest most point right there. So that's called the vertex. And of course, it's all discussed in the book. The other thing is that for any graph, we want to be able to, excuse me, we want to be able to say what the x and y intercepts are. Just like any graph, this is almost always something that we want to do. So for a parabola, you do want to say where the vertex is, and we almost read that off from the original equation, like that. So there's the vertex. I mean, you don't necessarily need to put vertex down here. I think that'll be fairly apparent. But we want to find the x and y intercepts. How do we find the x and y intercepts? How do you find the y-intercept? As always, how do you find a y-intercept? You make x 0. That's usually relatively easy. I mean, honestly, it is. Put a 0 in here. 0 plus 2 is 2. 2 squared is 4. 4 times negative 3 is negative 12. Negative 12 plus 5 is negative 7. So 1, 2, 3, 4, 5, 6, 7. Right there. So 0, negative 7. So the parabola roughly looks like this. And I'm not going to worry about whether your drawings are perfectly drawn. That's not really the issue here. How do we find the x-intercept? With any graph, you find the y-intercept by setting x equals 0 and the x-intercept by setting y equals 0. So we'll set y equal to 0 right here. Oops, 2 plus 5. And that's a quadratic equation, and we solve it. Now, at this stage of the game, I really don't care how you solve. You can solve it any way you want. You can solve it any way you want. I want to take a shortcut right now, and like I said before, I'm a little reluctant to take shortcuts because shortcuts don't always work. But there's a really nice shortcut for this. And you can multiply this out, add like terms, and complete the square. That always works. That's a guarantee. That's not a shortcut. You can multiply this out and use the quadratic formula. That's not a shortcut. That's a guarantee. But let me show you kind of a shortcut here. If I get this term on the other side, it's as if someone has completed the square. Look, divide both sides by 3. It's as if someone's already gone through the completing the step work for me, and I've only got a couple of steps to do. Square root both sides. And then subtract 2 from both sides. That's two numbers, but look at the graph. It crosses the x-axis in 2 places. And I think that it's more or less obvious that this is the point negative 2 plus the square root of 5/3. And this point right here, I'm misspeaking here for a second, but negative 2 minus the square root of 5/3. Now there is a y coordinate, so really there are those 2 points. Something you should be aware of or realize or understand is think about the square root of 5/3. 5/3 is 1 2/3, so the square root of 5/3. Let's make a note over here. The square root of 5/3. If you think about it just for a minute, it will become more or less obvious that this is greater than 1 and less than 2. 1 squared is 1, not enough. 2 squared is 4. We went too far because, remember, 5/3 is 1 2/3. Kind of goes back to a fraction thing again. As I discussed in the video when we approximated roots, in that video where we approximated roots. What does this tell me about this? Well, first of all, it tells me, let's say this is extremely roughly, at a very, very rough level. The square root of 5/3 is approximately 1.5. Now, it's not, you can throw it in your calculator and get a much more accurate approximation, but let's see, it's very roughly 1.5. Negative 2 plus 1.5 is negative 1.5. And that looks about right on the graph, and it should. And over here, negative 2 minus 1.5, negative 3.5. It looks about right. And now I can go one step further. Negative 2 plus 1.5 is negative 1.5, so negative 1, negative 2. That's where the vertex is. Negative 3, say negative 4, because I just said negative 2 minus 1.5 is negative 3.5. And that's approximately where it crosses right here. Approximately, roughly, not exactly, negative 3.5, and that looks right. So the graph all comes together, it all fits together, it all looks right. Okay, so anytime you make a graph, you want to find the x and the y-intercepts. If it's a parabola, you want to find the vertex. Now I'm going to release another video tonight because there's an additional complication. This is enough for now. This is relatively nice. Let me just throw in the other thing right now. I'm making the video, so let me just throw in everything. What else could make this more difficult or more challenging? Let me show you. And then, well, you still won't know everything about parabolas, but you'll know everything that we're going to talk about in this course. And let's say you wanted to graph this. Again, graphing parabolas, hey, YouTube is, I gotta say, YouTube is a great source. If you go to YouTube and search graphing parabolas or graphing quadratic equations, I mean, there's just 150,000 videos. I can't vouch for them, but you know, if you're usually on the front page, they're usually pretty good, and they'll show you the same things that I'm showing you. But let's say we wanted to graph this. Let's say 2 times x minus 1 squared. Let's say plus 3, just to keep the numbers nice and tame and reasonable. This one is shifted up 3 to the right 1, and it's curved up. Fine, no problem. You go about your business, you graph it. But just, I'm going to do something that you would never do. It's contrary to what you do. In fact, remember, what I'm about to do right now, don't do. But let's just say some evil demon came along and did this and multiplied this out. And then multiply this out and combine like terms. So x squared minus 4x plus 5. And you were told to graph that. That was your assignment, to graph this. Well, oh no, it's not in that nice form. So we have to put it into that nice form. And this is, it's not obvious how to put it in the nice form. It's not obvious. Maybe it's like coming into somebody's house and everything's messed up and they say organize, and you, I don't know how. I don't know how you want to organize. I don't know if that's a terrible analogy. Let me just show you what you have to do. What we have to do is we have to complete the square with a twist. And so here's how it goes. First step to complete the square is to get the plain number over on the other side. So that's exactly as it goes with completing the square. Second step was divide both sides by the coefficient of x squared. That's exactly as it goes with completing the square. The next step is to take the coefficient. Remember, this is exactly completing the square. Well, I mean, the y is coming along for the ride. I'm sort of pretending almost not to notice it. But take this, divide it by 2, 1 square 1, add that to both sides. So we add 1 to both sides. So far, everything is exactly as it goes with completing the square. Factor this, just like we do in completing the square. Bring this down here, sorry about that. Here's where the twist. Now solve for y. Solve for y. So there's the twist. Let's add this to both sides and multiply by 2. We add this, 3 halves, multiply by 2, 2 to cancel each other out. So you complete the square, and that puts it in this nice form. And then you graph it. So this is this additional wrinkle. Okay? And that's definitely enough for this video. Okay, test tomorrow, Friday, November 20th. You get a little over 24 hours to do it. That should be plenty of time. All right. Questions, let me know. I'll be on Zoom tomorrow. So if you have questions or email, text, some of you do on a regular basis. Some of you I haven't heard from. Okay, that's normal to be expected. All right.